Space-time, the stage on which our lives unfold, with 4 dimensions and curves above. We saw how this stage is integrated into the theory of relativity. Space and time are unified, and the dimensions of the stage are measured either with a clock or with a ruler. The question is, according to what script do the actors play on this stage? How do freely falling bodies move? How do rays of light travel? It's time to give the answer, Master Vanda. Most of the time, I live forgetting the physics I learned. I think about the space around me and the present moment, forgetting that my life is a journey through space-time along the world line that was given to me by the initial conditions of the Big Bang. Space-time is the stage of the universe, and atoms are its actors. I like to think about atoms, although the actors can be elementary particles or, in the macroscopic case, objects. The question is, according to what script do the actors play? By what rules do objects move in space-time? And for simplicity, let's refer to freely moving objects. We can already glimpse the key to the answer to this problem. Thus, we recall the equivalence principle, which we have restated as the motion of a freely falling body in the absence of all force fields. Except for the gravitational one, it does not depend on its mass or composition. In other words, in a gravitational field, the trajectories of a freely falling body are not determined by what is inside them, such as mass, color, and so on. And so, they can only depend on what is in their immediate vicinity, because we do not allow for instantaneous interactions at a distance. Well, for some freely falling bodies in their immediate vicinity, it's just empty space, which has only one characteristic, the metric g of space-time, which describes the curvature of space-time. Let's pause for a moment. Let's take a moment. Let's pause for a moment in hand. Its motion is not given by any force, as it was in Newton's time. Let's stop a moment to the let's pause that determines the motion. This also explains why the free fall of adjacent bodies is synchronized, regardless of the composition of the body. They share the same curved space-time around them. Once we agree that the motion of the body is given only by the metric of space-time, all we have to find is the law of this motion. How does a body move when left free in an arbitrary curved space-time metric? For this, let's observe that in Euclidean space, when no force acts on the body, not even gravity, the motion is straight and uniform. The trajectory is a straight line, and the world line will be the same if it is drawn in space-time. Minkowskian, the generalization of straight lines in a curved space, is a geodesic. It is by definition the line between 2 points that minimizes the distance, the shortest distance, and in space-time. There are geodesics that have the same definition, with the observation that they are either a minimum or maximum extremum. It then seems natural to assume, along with Einstein, that the motion of a free body in curved space-time follows the line of a geodesic, just as in Euclidean space it follows a straight line. Or, by generalizing one of the mechanical principles, we will say that a point-like body left free will follow a motion along a geodesic. In curved spacetime, where is it located? Let's not forget that through the same point in a curved space, several geodesics pass. Just as through the same point in a Euclidean space several straight lines pass, in the same way, through an event in spacetime, several geodesics pass that the free body can follow. The difference between them is given by the initial speed with which the body was thrown into space and the direction it takes. Each of the world lines that the body will follow after it is thrown will, however, be one of the geodesics that pass through that event in space-time. Let's now observe the power of generalization of the assumptions, because it doesn't talk about forces, but only about space. The proper time in which the body is found, as you might suspect, we will soon eliminate the forces, and our line of thinking will go something like this. Someone, let's see who, generates a curved space-time, and then bodies left free, or rather freely thrown, move in this curved space-time. Along the geodesic lines, we see that there are no longer interactions between bodies, as we used to think. Technically, we should mention that in space-time there are 3 types of geodesics: time-like, space-like, and null. Our example with the body will be for time-like geodesics, where the square of the relativistic interval between two nearby events is positive. Only on these geodesics can objects travel without equaling or exceeding the speed of light. That is why we need to complete our assumption. Freely falling bodies travel only on time-like geodesics, while light, on the other hand, travels on null geodesics. Here is a stylized example of curved spacetime. In case A null geodesic is shown for which the total length is 0. Of course, what I have told you seems simple in words. The mathematics, on the other hand, is more complex. For those interested in following the equations from the book, here is the basic idea. Here you see the equation for a geodesic. XMU represents the coordinates in space and time. Tau, the proper time, can be considered a parameter. And gamma are quantities derived from the metric g, which are called Christoffel symbols. An interesting exercise is calculating the motion of bodies freely falling on the surface of the Earth. We should get an accelerated motion, but that's not exactly what happens. If we follow the calculation from the book, which is not hard to follow, we first write an approximate equation of the geodesic, and then we simplify the terms and obtain an accelerated motion. See the last equation. Wow! So, the Newtonian motion of free-falling bodies is an approximation of motion in space-time along a geodesic. I think this is the most important message for today. Any free motion in a gravitational field is a free fall and happens along a geodesic in space-time. Why does the space station move around the Earth? It is always in free fall towards the Earth, and it ends up describing in space-time a world line, which is a geodesic. If only we could visualize these geodesics in space-time, how easy it would have been. In the end, here is a fascinating conclusion. We see here a clock orbiting around a star, like a planet. Its movement in space is the one in the middle, which describes a geodesic in space-time. However, the geodesic is an extremum, as we discussed in this case, a maximum. This means that out of all the trajectories between the initial event at the bottom and the final one at the top, this movement is the one that gives the clock the longest distance, which for the clock is measured by its proper time. Thus, if the clock follows the trajectory on the right, it has to travel at a high speed to return to the final event. At the moment determined by us, the rapid movement would have made them tick more slowly. According to the theory of special relativity, the proper time between the two events would then have been less, 3 hours in the figure. If the clock had had to follow the orbit on the left, it would have gotten too close to the sun, and again, it would have ticked more slowly, 1 hour in the figure, due to a time dilation effect in a gravitational field, which we will describe later. To maximize its proper time, 6 hours in the figure, the clock will follow the middle orbit given by the geodesic line in space-time. I like to think about this conclusion by telling you that the clock wants to pass, to live longer. Who wouldn't want that? And the clock does just that. Between two given events in space-time, the initial and the final one, by choosing the geodesic. Here's an example. On the left, there's a sketch of a clock thrown upwards in such a way that it falls back exactly after a time equal to 2 seconds. On the right, the world line of this motion in space-time is sketched with a thick line. Notice that the horizontal axis is time. A dotted line sketches another world line positioned infinitesimally close to the real one. Among them, the clock chooses the one for which the relativistic interval is an extremum, meaning the proper time shown on the screen is maximum. How much is this time gain? For infinitesimal fractions of a second for this infinite time gain, the clock chooses to follow a geodesic. Of course, this is a poetic observation, because we should remember that the clock doesn't actually choose anything. Until next time, please subscribe if you haven't already by clicking this subscribe button right now. I want to thank those who support us on Patreon and those who become channel members here. I'm Christian Prasura, Physics Explained. You are cool, and I wish you all the best. Goodbye.